In this video, we're going to be taking a look at 3.2, basic differentiation rules and rates of change. So previously, we've tied limits into this idea of the derivative, which is the slope at a single point of a function. And we've used the definition for the derivative to find the derivative. Remember, the limit as change in x approaches 0, f of x plus change in x plus f of x all over change in x. And essentially this was the slope at a point. Given change in x, we want it to approach 0, so we want the 2 points to become 1. That's why we had to set it up as a limit. Today, we're going to learn the differentiation rules. Now, there's all sorts of differentiation rules, but they're all tied to this idea right here, right? So this right here is the grandmaster. Don't forget about where all of these rules came from as we go and learn them. So first of all, the constant rule. And this one makes sense if you think about back in the algebra. Think about it. If you had an equation with the slope, the equation of y equals 7, right? So let's look at this. What is the slope of that graph, right? It's got a slope of 0. So when you are finding the derivative of a constant, c is a constant there, the derivative of a constant, that's how that part reads, it's always going to be 0. Let's look just below here. On the right side, these are all different ways to show the derivative. So remember, it's the slope at a point. So on all of these, since they're all constants, all of these are constants, 9, -3, 4, and even down here, pi is a constant, okay? And then also we're told that k is a constant, so the derivative of that is also 0. Okay, so now let's take a look at the power rule. This is the one thing that calculus students will use the most for the rest of the year. So you could say this is the most important thing. I don't think it's the most important thing, but you'll probably use this the most out of everything that we learn the rest of the year. So we have a function, x to the n, right? That's any polynomial rational function, and it is differentiable. It has to be differentiable. We've been talking about when functions are not differentiable. This has to be differentiable at the point that we're looking at if we're looking at a specific point, okay? Then down here, the derivative of that function is equal to x to the n minus 1. Oops, I forgot one point here, sorry. It's n times x to the n minus 1. So rewrite that if you need to. It's n times x to the n minus 1. So that is the power rule. Just have that down for right now. And we're going to go ahead and do an example of the power rule. So down here, you have y is equal to x to the 16th. Okay? And y is equal to t squared plus 2t minus 3. Now we're going to use the power rule to find the derivatives. Now using the power rule, what you end up doing is you're taking the exponent and bringing it down and multiplying to the variable. So it would be 16 times x, and then you'll end up just subtracting 1 from your variable, and that is your new exponent. Or sorry, 1 from your exponent, and that is your new exponent. So then the derivative then becomes 16 times x to the 15th. And that's it. So right here, we have the derivative. So in general, let's look at this example. In general, all of your terms, so there are 3 terms there, all of your terms are going to be, the exponent is going to be 1 less. So this is going to be minus 1. Since this is to the first, it's going to be minus 1. Okay, and then also you're going to bring the exponent down and multiply. And again, this is to the first, you're going to bring it down and multiply. That is a constant. And we already talked about what the derivative of a constant is. And when you're using the power rule, you differentiate or you apply this power rule to each individual term. So again, there are 3 terms here, and we apply the power rule to each individual term. So it's going to be y is equal to 2t, then 2 minus 1 to the first. Plus, then we apply the power rule. 1 times 2, that's 2. T, 1 minus 1, that's 0. And then this is a constant, so you could put minus 0. So now, let's go ahead and just rewrite this. This is just 2t. And then here, t to the 0, anything to the 0 power is 1. So 2 times 1 is just 2. And so now, the equation for the derivative, these are the equation for the derivative, is y, the derivative, is equal to 2t plus 2. This is the equation for the derivative. Okay. All right, so that's the equation for the derivative right there. And before, we would have to do this. Again, don't forget the limit where all of this came from. It's extremely important. So before, we would plug it into here and we would get the equation for the derivative. But now we learn the power rule, which makes it a lot easier to find the derivative. And everything that we learn in here is based off of patterns. So if you just kind of look at the patterns of what we would do is find the derivative of several functions, of polynomial functions, and you can see the patterns, and it applies to this rule. So let's go ahead and try that. On this example, find the slope of x to the fourth minus x at the point -1, 2. Go ahead and pause this video, try this on your own, and then come back and see how you did. Okay, so let's see how you did. So first of all, I just rewrote it, giving the exponent to the second term of 1. And then when you find the derivative, you would bring that exponent down, multiply it out front. That's where that 4 comes from. Subtract 1 from the exponent. That's where that 3 comes from, minus x to the 0. So, or 1 times x to the 0. So when we rewrite it, here is our equation for the slope, but they give us a point. Okay, so at that point, and I use function notation to show that we're plugging -1 because that's where we want to know the slope at. We plug that in, and the slope at -1 is equal to -5. Okay, let's go ahead and try another one, finding now the equation of the tangent line. So we're going to do the same thing that we did up there, but one step further, using that slope and that point. So you're going to use this slope and that point, or in this case, it's the same problem, so all of that's done. So now you're using that slope and that point to find the equation for the tangent line. Again, you notice it's the same equation, same point. So we did all of the work up there, use that to find the equation for the tangent line. So like I said, we did most of the work up above, so we're going to just start right here where we have the slope of -5, and there's our point. Plug it into the y equals mx plus b. We know what our y is, what our x is, what our slope is, and we get b is -3. So our final equation should be y is equal to -5x minus 3. Okay, so now let's take the power rule one step further with this thing called the constant multiple rule. So it's essentially the same thing, but it's saying, hey, listen, if you're finding the derivative of a function that's being multiplied to a constant, right? That constant doesn't change anything, but it's going to be that constant times whatever the derivative is. So if you're going to bring that exponent down, you multiply it to that constant. Okay, we're going to try some examples, but there's what the definition for the constant multiple rule looks like. Now let's do some examples. So if we look at the first one, 1 over x to the 8th, I'm going to change this so that it's y is equal to x to the -8th. Now we can apply the multiple rule, or sorry, the product rule. And when we do that, or the power rule, when we apply the power rule, we would take this -8, you would bring it down and multiply. So the derivative is going to be -8 And the constant out front right now is 1, so it's just negative 8 times 1, or negative 8. X, and remember, you're subtracting 1. So when your exponent is already negative, it's going to be negative 8 minus 1, or negative 9. And you can even rewrite this as negative 8 over x to the 9th. And this would be our final answer. That's as far as we could get. And that looks like a 7, but that's a 9. All right, now on this next one, when you have this function, I'm going to break this up. So right now we don't have any ways to find the derivative of this. So you're going to have to break it up into two polynomials, two individual functions here that we can differentiate using the power rule. So it'll be x to the third over x squared minus 6 over x squared. Okay, so that is the same thing as this function above, but now I can differentiate both. So let's just rewrite them. This can be simplified down to just x, and this is 6x to the negative second. Okay, we want to write them in a way that we can apply the power rule. So now we're going to find the derivative. The derivative of x is just 1. And then you're going to bring this negative 2 and multiply it down there to that 6. And when you do that, negative 2, you can bring this negative in there and say negative 2 times negative 6, that's a positive 12. And then x, and remember, you're subtracting 1. So negative 2 minus 1, that's negative 3. And if we didn't want to write it with negative exponents, it would be y is equal to 1 plus 12 over x to the third. And then that would be our final answer on that one, as far as we can go. All right, now using sum and difference rules. This is similar to the constant rule. It's pretty straightforward. It makes sense. The sum and difference rule basically says that, hey, listen, if you're taking the derivative of a bunch of terms like this up here, we have these two terms right here, just find the derivative of each individual separate term, okay? And you would just go through and do that. Go ahead and try that for the next one here. Pause the video, try it, and see how you do. All right, so when we do this, we end up getting, remember when we find the derivative using the power rule, we're going to bring this down and multiply. So that's where that 4 came from. That's where that 3 came from. And you can imagine there's a 1 up there. So when you multiply 5 times 1, it's just 5. Okay, and this is a linear, so the derivative of 5x is 5. The slope of 5x is 5. So now we have this. Let's go ahead and simplify. When we multiply these together, you would have the derivative, it's just going to be, because those 4's will cancel, that's just going to be 3x to the third plus 6x squared minus 5. So our final answer is going to be right there, 3x squared plus 3x to the third plus 6x squared minus 5. Now for the derivative of sine and cosine. So make sure you get these written down. Sorry, I didn't leave much room here, but the derivative of sine, so d over dx of sine, the derivative of sine is cosine, and the derivative of cosine is sine. And throughout this chapter, we will look at a lot of examples of sine and cosine, but if you look at the graphs of sine and cosine and think of, hey, looking at the graph of sine, thinking, hey, what's the derivative at this point? And then you look at the graph of cosine, that tells you the derivative at that point. And this is, negative sign. And then if you look at the derivative of cosine, and think, hey, what's the derivative at this point? It's equal to whatever the y value at negative sine is. So we're going to look at that quite a bit throughout this chapter. But go ahead and try some of these on your own, these next 3 right here. Go ahead and pause the video and see if you can't do some of these using the power rule, the sum and difference rules, everything that we've learned, and try these on your own. Okay, so if we take a look at these, first of all, the derivative of cosine, remember, is negative sine. So right here, this constant stays out front, but then cosine changes into negative sine. So the derivative is going to be negative 2 sine of x. On the next one, find the derivative of each individual term. So we're looking at those two terms. The derivative of x is just 1, and the derivative of sine is cosine, so nothing changes there other than sine changes to cosine. So the derivative is 1 minus 2 cosine x. Let's look at the last one here. Derivative of cosine is negative sine, so the derivative of 1/2 cosine is negative 1/2 sine, and derivative of sine is cosine, so derivative of sine is cosine there, so that becomes then the derivative is negative 1/2 sine of x minus cosine of x. And a lot of times you can put these in parentheses. I know a lot of people would rather have those in parentheses to clean it up a bit, and that's fine. Later on, when we have functions inside there and we have composite functions, we definitely want to use parentheses. So maybe use parentheses even though I'm not here. All right, looking at derivatives of exponential functions. I think for right now, for the exponential, we're just going to look at e, just in case it comes up. But it's really easy. If you have y is equal to e to the x, the derivative of that is itself. That's why e to the x is so interesting and so amazing, because it is its own slope curve. Okay, and that's all you're going to need to know for now. Later we'll do actual exponentials or other exponentials where e for the base is something other than e, but for right now that's all that you're going to need to know. So now if we take a look at this idea of average velocity. Now, average velocity, please don't get this confused with velocity, because average velocity, that's essentially the slope of the secant line, not the tangent line, because average would be like from this point to this point, what's the average? And that would be the slope of the secant line, this average speed. All right, so that's kind of what we're looking for. On this first one, a soccer ball is dropped from a height of 250 feet. Its height at time t, given by the position function, s is equal to negative 16t squared plus 100, where s is in feet, t is in seconds. Find the average velocity over each of the following intervals. So let's see what you can remember back from Algebra 2, probably would have been the last time you did something like this. Go ahead and try these on your own and see how you did. Okay, so on the first one, when we set that up, remember it's y minus y over x minus x, and that's where we're finding that slope of the secant line. So you end up with something like this, and those hundreds are going to end up canceling. So really, you would just have negative 16 times 4, which is 64. So negative 64 minus, and then this is just going to be negative 16 times 1, which is negative 16. So negative 64 plus 16 all over 1. And then when you combine those, you end up with negative 48. So on this first one, the average velocity is negative 48 feet per second. And if we take our time and set up the next one, again, you notice these hundreds will end up canceling. So you can just look at those other terms. Take 1.1 squared times negative 16 minus a negative 16 or plus 16 all over 1.1 minus 1, which is 0.1. And when you simplify all of that, you'll end up with negative 3.36 all over 0.1, which is, this is dividing by 10, so that's going to be negative 33.6 feet per second. Right, because this is one tenth, so dividing by 1/10, which is the same as multiplying by 10. Okay, let's try one more. So on this one, we set it up. Again, take our time setting it up. But at this point, you should know that those hundreds are going to end up canceling. So it's going to be negative 15 times 1.5 squared minus 16, and negative, that's a negative 16 times 1 squared. And you end up with negative 20 over 1/2, which is the same as multiplying by 2. And so our final answer is negative 40 feet per second on that one. And again, we're finding average velocity, so there's nothing about calculus here. It's the slope of the secant line, not the slope of the tangent line. Now, if we wanted to know the velocity at a specific point, that's where calculus would come in. But here, we just wanted the average velocity. So over a certain amount of time, what's the average speed? That's an algebra style question. And here is a calculus style question because we want to know the speed at a given time. So these two times are at 5 seconds and 10 seconds. Our function is given to us up here. That's our position function. And they give us the initial velocity. Go ahead and it says from the surface of the Earth. So that gives us our initial position as well. That's s sub 0. And so go ahead and try this on your own, finding both the slope at 5 and 10 seconds or the speed at 5 and 10 seconds. Okay, so here, when we find the derivative with the initial velocity of 120, your derivative is negative 9.8t plus 120, applying the power rule. In the future, this is the change in position, but you should also be aware that this is the velocity, so v of t. So this gives us the speed at any given time, and we want to know the speed at two specific times. And those two specific times are 5 seconds and 10 seconds. And so when we plug those into our velocity or change in position equations, you get 71 meters per second at 5 seconds, 22 meters per second after 10 seconds. And that is all for 3.2 basic differentiation rules and rates of change.